So midsegments are segments that are joining the midpoints of two sides. So we're still looking at a triangle, still looking at triangles here, but now we are connecting the midpoints of two of the sides. And we're on page 330 here. Okay, in that picture box, go ahead, draw yourself a triangle. Doesn't matter what type of triangle it is. Any type of triangle will work. So it doesn't matter whether it's right, acute, obtuse, whatever you want. But we've got a triangle. And we are talking about midpoints of the sides. So I want you to go ahead and find the midpoint of all three sides here. Find the midpoint of all three sides. Go ahead and eyeball it. Of course, we can make sure that it's a midpoint by just throwing up some tick marks. So we're looking at those three midpoints of our sides. And then what we know about midsegments, what we see from our definition there, is the midsegment is the segment joining the midpoint of two of the sides. So if we take those midpoints that we have and we start connecting them, that's going to give us a midsegment. So if I connect two of my midpoints, that's going to give me a midsegment. Okay, that's considered a midsegment. Now, I'll draw in the other ones in a second, but I want to talk about this because I want to start talking about what our theorem is going to tell us about midsegments. Okay, and there are three midsegments, just so we're clear. There are three from here to here, here to here, here to here. I'm just not going to draw in those other ones because right now I want to concentrate on this one. So if I'm going to look at this and I want to see what do we think we can say about this midsegment compared to the rest of the triangle. I'm going to start putting letters down here just so we can reference some stuff. Okay. Any ideas on what we think we might be able to say about that midsegment, about DE? We can type it in, we can say it.
It's half the length of the bottom segment.
Yeah, it is. You're absolutely right. It is half the length of the bottom segment, right? So DE is going to be half the length of BC. Well, half the length of BC has that 2 tick mark right now. So I can say that DE is going to be the same length as BF and FC. It's going to be the same exact length. Good. So that's one of the things that we can say. There's one more thing that we can say, and then I'll show you the theorem and we'll write it down. We'll get it word for word. We're just talking right now. So that's one of the things we can say. Any ideas on what the other thing we can say is?
Are all three of them congruent?
All three of these are congruent. All three of these are. Not all three midsegments are. But this is congruent to this and this. The three midsegments are not.
Oh, okay.
They would be if it was an equilateral triangle, but otherwise no. Good thought, though. What else can we say about DE compared to BC?
Is
Parallel, there you go. Somebody typed it in the chat. I saw it. I think Kara said it. They are parallel. They're parallel. DE is going to be parallel to BC. Okay, and that's always going to be the case, where the midsegment is going to be parallel to that other side. Okay, so they're parallel, and the relationship of the lengths we also know. This is going to be half of this. Okay, let's get some words down. Let's get our theorem down in words here, so that we have it. There's no point of concurrency for this one, right? There's no place where those three midsegments are going to cross at one point. So we don't have a point of concurrency, but we do have a theorem. So let's go ahead and copy that down, the triangle midsegment theorem. So our triangle midsegment theorem tells us that a midsegment of a triangle is parallel to a side of the triangle and is half the length of that side. The midsegment is parallel and half the length of one of the sides. Another couple seconds, copy that down if you're not done yet. All right, so we know it's parallel and it's half the length of that side. So let's take a look at our drawing again. And I drew in the other two midsegments here. Okay, because this is always going to be the case no matter which midsegment you draw in. We know that that theorem is going to hold true. So for example, if we look at EF, right? We look at EF. I know EF is going to be parallel to AB, right? It's parallel there. And we also know that it's going to be half of AB. If it's going to be half of AB, that means it's also going to match up with each one of these segments, right? If it's half of AB, it's going to be the same thing as BD. So it's going to be there. If I look at DF, DF is going to be parallel to AC. Parallel to AC, right? And it's going to be half of AC, which means I've got 3 tick marks there because DF is going to be the same length as EC because it's half of that entire side. So a lot of things are going on here, right? A lot of tick marks are going on. I want you to pick one of the small triangles. I got 4 small triangles here, right? I have 4 small triangles. Pick one of them. Doesn't matter which one. I want you to look at that. One of those triangles, whichever triangle you're looking at, I guarantee you has one side that's 1 tick mark, one side that's 2 tick marks, and one side that's 3 tick marks. They all do. Right? All of them have that. And since all of the triangles have the same 3 sides, that means that all 4 of these triangles are congruent. All 4 of those triangles are congruent, side, 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 right? So all 4 of these are congruent. That's going to help us to solve some stuff. If we know that all 4 of those smaller triangles are congruent, including the middle one, which we'll give a name for in a second on our sheet. But if all 4 of these are congruent, that means we can start solving stuff dealing with angles as well. Now, I don't think you're going to see too many angle questions today, but eventually we might see those angle questions come in. I know if I look at this angle, right? I look at this angle, EFC. Knowing that these 4 triangles are congruent, I can now say that this angle has to be the same, that this angle has to be the same, and that this angle has to be the same. Okay, because they're all congruent. CPCTC. Of course, there are other ways that we can get there, right? Because we know these lines are parallel, I'm looking at corresponding angles there. Because I know these lines are parallel, this is the alternate interior, this is AIA here, it forms that Z shape, right? Same thing over here, I got a Z shape here to say that these 2 are congruent. So there are other ways that we can get there, but once we know and realize that the 4 triangles themselves are congruent, we don't have to go through AIA and corresponding and all of that. We just know that they're going to be the same, that all corresponding parts are going to be the same. So that's going to help us solve some stuff out. Okay. All right. Let's finish up that page. told you that I would give you a name for that middle triangle. That middle triangle is called a mid-segment triangle. A mid-segment triangle, all three mid-segments together. So that is the mid-segment triangle in the middle. All right, so let's take a look at what types of questions we're actually going to see about this, because we know what we need to know. We know the two things the theorem tells us. The theorem tells us that it's parallel. The theorem tells us that it's half of that parallel side. So whatever this is, that's half of it, right? So we know that. But let's look at, in the book, what they're going to ask us to do. Because they're going to ask us to do a couple different things, some of them easier than others. We start off with probably, well, I won't say that it's difficult, but probably the most work that we'll have to do will be in this first type of question here. Erase the other stuff. So this is basically a coordinate proof. We don't have to get into a whole bunch of stuff on it, right? But it technically is a coordinate proof because we're proving something in a coordinate plane. It says in the big triangle, JKL, show that mid-segment MN is parallel to JL and that MN is half of JL. Basically what we're doing is we're proving the triangle mid-segment theorem. We're proving that theorem. We're proving those two things that it tells us. Well, we need to show two things. We need to show that it's parallel. To show things are parallel, we need to find the slope. We need to show that they have the same slope. So all we would have to do is in the picture, and they will give you the picture, I believe. If not, then sketch it out, right? Draw it out. But we just have to find the slope. And you have to show that the slopes are the same. From M to N, that's down 1 over 4. That'd be a negative 1/4 slope. From J all the way to L, that's down 2 over 8. Down 2 over 8 simplifies down to negative 1/4. They have the same slope. They're parallel. So that's the first thing. The second thing is showing that MN is half of JL. That's talking about length. That's talking about distance. We would have to do distance formula for that. So this is why I say this one probably takes the longest, just because we have to do some distance formula there. Okay. So you would do distance formula. If we did distance formula, we have to find those points, right? -4, 3, and 0, 2. I'll show you distance formula just because even though we do it seemingly every other week or so, we still forget. So we got to subtract the x's, we got to subtract the y's. That's going to give me a -4 squared plus a 1 squared, which is going to be the square root of 16 plus 1. I'm looking at the square root of 17. Now, you could put that into a decimal, or we could just leave it as square root of 17. Okay, either way. I'm going to leave it as square root of 17. So then I'm going to find the distance from J to L. I've got my points already listed there. So we're looking at -6 minus 2. We're looking at 1 minus a -1. That's going to give me -8 squared plus 2 squared. I'm looking at 64 plus 4. I'm looking at the square root of 68. Now here's where people get a little confused. Okay, we did distance formula, we found these. But we know from our theorem that this MN is supposed to be half of JL. 17 is not half of 68. It's not. We know that. If you were to type these into the calculator, you would see that this is half of that. Okay, you would see that. The other way that we can get there is by simplifying the square root of 68, simplest radical form. And I know it's been a while since we've done simplest radical form. Okay, we're going to get more into it again as we move on throughout the year here. But it's been a while. The square root of 68 remember you find a perfect square factor. That's 4 times 17 is 68. Your perfect square factor. So the square root of 4 is 2. Can't do anything with the 17. So now if I look at those two, now it's pretty clear that this is half of this, right? Because this is 2 times root 17. This is just root 17. So if we do simplest radical form, it'll jump out to us. Or, again, like I said, if we type this into the calculator, this is probably going to give us 4.1. This is going to give us 8.2 then, if we do that. And again, rounding might change it, right? It might be slightly off, whereas the or the square root is an exact number, so we don't have to worry about rounding. All right. So again, this is probably the hardest, the longest problem that we're going to have to deal with. The other ones that we're going to see are more straightforward. A lot of it is just identifying stuff, identifying what is parallel to what is half of what, right? What's congruent to what, this sort of thing. They got this really cool triangular lunch plate tray thing that they show you, so that's cool. Probably not ideal, but anyway, so these are the types of problems that you're going to see, right? Just using that theorem, what's parallel to what, what's congruent to what. There is one more that I want to point out to you. We'll point out number 17 here. Okay, so I want you to look at that. We've seen questions similar to this before. We saw these when we were dealing with centroid. But now we're dealing with our mid-segment. And so we've got when AB is equal to 3x plus 8 and GJ is 2x plus 24, what is AB? So we know this is going to be 3x plus 8. And this whole side right here is 2x plus 24. So if we think about our theorem, we think about what we know that this is half of that. So 2 ways that we can do it. We can cut this in half and set it equal to this, right? In which case, cutting this in half, each half would be x plus 12. So if half of this is x plus 12, we know that's congruent to this. So we can say that's equal to 3x plus 8 and solve it. Or what we can say, and that works great because this is divisible by 2. If this isn't divisible by 2, I wouldn't do it because then you're getting fractions decimals. The other way that we can do it is we can take that smaller one and times it by 2. So if we take that smaller one, that 3x plus 8, we times it by 2, then we can set it equal to the whole thing. And we can solve it that way. So either way there is going to work, right? You distribute, you solve it out, you get your answer. Then, of course, just make sure they're not asking what x is equal to, they're asking what AB is. So after you solve for x, we got to plug it back in and get that. Okay. All right. Great. Any questions about this?